Earlier on in this chapter, we learned about the fundamental theorem of variation. It simply said if we have a direct variation equation, that whenever we multiply x by some number c, then y will also be multiplied by c. If we had an inverse variation equation, then if we multiplied x by some number c, then y would be divided by that number c. Well, today we're going to take a look at using the converse of the fundamental theorem of variation to help us find a model that fits our data. Now remember, the converse of a statement is simply switching the if and the then. So now if you take a look here, we see that the converse states if x is multiplied by some number c and y is multiplied by some number c to the nth power, then it is a direct variation equation that follows the form y equals k times x to the nth power. And likewise, if x is multiplied by some number c and y is divided by some number c to the n, then it must be an inverse variation that follows the form of y equals k divided by x to the n. So let's take a look at a few examples and see if we can figure out how to use the converse of the fundamental theorem of variation to predict a model that fits our data. In our first example here, we're given a table of data, and we're asked to use the points 1, 5, and 2, 20. So here's G, it's going from 1 to 2, and M is going from 5 to 20. So ask yourself, what's happening to G? It's being multiplied by 2, it's doubling. Well, what's happening to M? And as G doubles, we say that M is being multiplied by 4. Or another way to state that is 2 squared. All right, now let's check out the data points 220 and 6, 180. So here's 220. And here's 6, 180. G is being tripled, or in other words, multiplied by 3, and M is being multiplied by 180 over 20, which is 9. Now, in other words, as G is tripled, M is multiplied by 9, or 3 squared. So take a look at the pattern that's forming here. We say that M varies directly as the square of G. So I can write my direct variation equation that states M varies directly as G squared. Okay, now let's see if we can use our data to find a value of K. Let's simply take one of our data sets. 220 will work. So we're going to substitute in 20 for M, K times 2 squared. Well, 2 squared is 4, so I need to divide both sides by 4. And my value for K is going to be equal to 5. And therefore, my direct variation equation that models this data should read as such: M equals 5 times G squared. And now I can use that variation equation to predict other values for M when I know G. All right, let's take a look at example 2. Again, we have another table of data values here, and we're going to see if we can use the converse of the fundamental theorem of variation to find a model for that data. So let's pick some points here. Let's start off with taking a look at P, as P goes from 1 to 2. It's being multiplied by 2. Well, what happens to Q is exactly the same thing. It goes from 4.5 to 9, which is it's multiplying by 2. Does that same pattern occur when I go from 2 to 6 for P? In other words, it's being multiplied by 3. And then Q is going from 9 to 27.1. So that's approximately a multiplication by 3. So you can see that this is a direct variation equation, and the model that implies is simply y equals k times x. It's not being increased by any powers. When you double one variable, it doubles the other variable. So this simply implies that we have a direct variation equation of y equals k times x. And now we're going to take a set of data points to see if we can find the constant of variation. So I'm going to actually write this in terms of p and q. Q is my dependent variable. So q is equal to k times p. We'll substitute 9 in for k, or sorry, 9 in for q, and that's k times 2. Divide both sides by 2. Our value for k is 4.5. So that leads us to the equation q equals 4.5 times p. And that's our direct variation equation that models this data. Okay, in our next example, we're again given a data set and we're asked to consider the weights and the distances away from the center of a seesaw that is needed to balance these weights. Well, we're going to start off with the data points 2.5, 18, that's this one here, and 5, 9. W is our independent variable and D, our distance, is our dependent variable. So as we double W in order to go from 2.5 to 5, we see that D is being divided in half. So when W is multiplied by 2, D is being multiplied by 1/2. In other words, now these are inverse operations. One's being multiplied, one's being divided. So keep that in the back of your mind. This implies this is an inverse variation equation, and most likely it will follow y equals k over x. But we have to test some points out to find out if this is the correct model. So let's do that. We're going to take a set of data points from our equation, or from our table. We'll say W, which is our independent. So we'll say D is our distance is equal to K divided by W. There's our model. Let's substitute in some known values, such as 9 equals K over 5. Now I need to multiply both sides by 5. Constant of variation is going to be equal to 45. Okay, so my model now should read distance is equal to 45 over my weight. So let's just take a look at another set of data points from our table to make sure that we have the correct model here. And if I take a look at this one here, it says 10 and 4.5. I see that 4.5 should be equal to 45 divided by 10, which it is, so I have the correct model. And now I can go about answering question part C that asks me to find the distance needed to balance 22 pounds. So I'll take 22 and substitute it in for W and solve for distance. When I do that, I'll have 45 over 22, and that results in 2.05.